Hey everybody. So we're going to look at a small proof using fundamental theorem of arithmetic. So what we're looking at here is we're going to say let P be a prime number and N and D are natural numbers and D is a factor of P to the N. Okay, so that's what we're looking at. That's the statement, the initial statement. What we want to prove from that is that if D equals P, that should be an M. Let's make that a little clearer. Okay, that's not clear. Oh, that's weird. Okay, there we go. So prove that if D equals P to the M for some natural number M, show that 0 is less than or equal to M, which is less than or equal to N. So M is basically between 0 and N. So this is probably pretty obvious. I'm sure you can, if you have an intuitive sense of the fundamental theorem, that makes sense right away. But let's talk through it. Let's consider an example first. So an example, like I can look at 125, and there's only 4 possible factors, 1, 5, 25, and 125. So 5 obviously being p to the third. And so we've either get p to the 0, p to the 1, p to the 2, p to the 3. So 5 in each of those cases would be the prime number that we're looking at, obviously. So let's just give us an example of how it kind of sets up. So the way we're going to do this is we're going to start by saying, let's show that if Q is a different prime, so we're picking out a different Q, and Q is not equal to P, okay, then Q can't divide D. Okay, so we're basically looking at another one here. So let's assume, so we're going to use a proof by contradiction here. And so let's assume that P actually does divide, or I'm sorry, let's assume that Q, rather. Let's assume that Q does divide D, okay? And we know already, because we were given, that since D is a factor of P to the N, that D divides P to the N. Well, it follows that if Q divides D and D divides P to the N, then Q divides P to the N. But remember, we've defined P as a prime number, and since the number we're looking at here is just the prime number P raised to a power, by the fundamental theorem of calculus, if Q is another prime number, this is a contradiction, because we can't have another prime number Q dividing a power of some other prime. So contradiction of the fundamental theorem of arithmetic. Okay, so we've established basically that the only factors of, or the only prime numbers that are part of P to the N are P. There is no other ones in there. So that's the first part of it. The second part that we're going to look at now is then this basically says so that only D can divide P. Okay, and by the FTA, by the fundamental theorem of arithmetic, D equals P to the M. It's some power of P, because there can't be any other prime numbers in there. And now the only other thing we need to show then is that M actually has to be less than N, which is pretty straightforward, because if M is greater than N, then it follows that P sub M should be greater than P sub N, but we've just said that D is P sub N. And if this were the case, then this contradicts the statement that D divides P sub N. Okay? So, and basically there we're done. So therefore, 0 has to be less than or equal to M, which is less than or equal to N. So M is in between them. So we've established essentially that if you have this prime fact, this number, which is made up of single prime to a power, that any divisor of that, any factor of that particular prime is going to be some other power of that prime number, up to and including the number itself. Okay, that's essentially what we're trying to prove here, and we use fundamental theorem in a small way to help us do this with a couple of proofs by contradiction. So hopefully that makes sense. Just a small proof to give you an example. Okay, if you have questions, please ask.